All right, in this second video, we're going to talk about eutectic cooling in ternary phase diagrams. All right, so here's a ternary phase diagram I've shown you before that has a eutectic reaction in it, labeled E. And I wanted to go through these, what we call crystallization paths, to kind of show you the progression and the reactions that occur throughout this diagram. And so a couple things to point out is the composition of the material that we're working with is X. So that is our composition of the material. And then the eutectic point is labeled, and it's right towards the center. I've also labeled some of the temperature contours as well. And then the primary phase fields, alpha, beta, and gamma are labeled here as well. So we're going to talk through this path and so forth, but that's the thing to kind of keep in mind as we go through this. All right, so since we're talking about eutectic cooling, the first thing that we're going to think about is this composition if we have it at a really high temperature. So basically high enough where we have 100% liquid, right? And so that occurs in this composition at roughly 635 degrees Celsius. And so the reason I knew this is because, again, the temperature contours tell us the liquid composition, right? So if I look at this diagram, this is the 300, 400, 500, 600, and then this is the 700 temperature contour. So I'm in the middle of it. And so again, somewhere around 635 is where I'm at right here, right? So at that composition, at 635, I would just start to form a solid phase denoted by the primary phase field. But above that, that tells me that I would have 100% liquid. So if I have a composition of X, so I have those amounts of the components A, B, and C, and I'm above 635, then this thing is 100% liquid, is what this diagram tells me. So that's the first part of it, and that's sort of where we go from there. So beyond that, though, below that is where it starts to get interesting. All right, so at 635, that is where this composition hits the liquidus surface. So that tells me, again, by definition, that I would start to form a solid, and that solid would be denoted by the primary phase field. So in this case, alpha, because I'm in the primary phase field for alpha. So I should start to get alpha when I hit the liquidus, and that is at a temperature of 635, right? So my first reaction then, and it's going to be shown here on path 1, is going to be, I have the initial liquid, and that is transformed into the solid alpha plus a liquid, and I call that L prime because the liquid is of a different composition. And so in this case, I'm in a two-phase field, right? Liquid plus alpha, and I can get the amounts of liquid in alpha after or lower than 635 by using the binary lever rule, right? Keeping in mind that alpha has a composition of A, and then the liquid is going to change compositions with temperature, right? But we know that the composition is going to change, and it's going to be a function of temperature denoted by the temperature contours. So I can determine the liquid composition based at what temperature I'm at. And so that's going to be how I determine the amounts and how I determine the liquid composition to determine those amounts for that calculation. All right. So for example, I can do a calculation here. So again, this, right when it encounters the liquidus is at 635. This is the temperature contour for 600, and then this one would be for 500. So let's say that I'm at 500 degrees. So that would mean that the liquid composition would be Y. right? Denoted by the temperature contour. My solid composition would be A. And therefore, I have my solid composition, I have my liquid composition, and I have my alloy. And so I can apply the binary lever rule to get the amounts at that point. So the main difference here, and what we have to keep track of, is that our liquid composition changes as a function of temperature. And so we want to be able to determine what that is and show that graphically on this curve. So you'll notice that the green curve, or the green arrow that I've shown here, going from X down to this point here, down to the boundary curve, represents the changing liquid composition with decreasing temperature. That's what I'm showing here. So this is our crystallization path. It basically tracks the liquid composition as a function of temperature. And so that's what we're going to be showing along this crystallization path. So this is the step one. So this is path step one, and this is the reaction. This is kind of what you can see schematically happening for that reaction. All right, so we've talked about this first step. Basically, once this liquid composition reaches this point. So at this point, we see that we've encountered the boundary curve, right? Basically the intersection between two primary phase fields. So this, again, by definition, told us that we had a liquid in equilibrium with two solids, in this case alpha, but now also gamma. So this tells us that once we reach this point, so once we intersect the boundary curve, we start to form a new phase, and that new phase is gamma. So basically from this point Z on, we form gamma. And so that's what path 2 is showing us. We have that new liquid, L prime, and we're still forming alpha, but now we're forming gamma. And then again, we still have liquid, but the liquid has a different composition. So we're going to call that L double prime. So this is going to be during the second sort of path here, starting at Z. And so at that point Z, if you recall, we just talked about there's 3 phases in equilibrium. And so I've also made this triangle here, right? So this, in essence, is the triangle that you could use to calculate phase amounts, right? Since we have liquid phase represented by Z, and then alpha, and then gamma represented by A and C. So that is basically our triangle for determining those 3 phases, starting at this point. But again, if we wanted to know it at a lower temperature than 400, then we would have to account for the changing liquid composition. And the way it changes is denoted by the green arrow now. So I've moved that green arrow. So now starting at Z, what's going to happen is the liquid composition went from X, followed that arrow down to point Z, and now that liquid composition is actually going to trace the boundary curve. So basically the liquid composition is going to follow the boundary curve now. All right. So again, with decreasing temperature, we're going to follow the boundary curve. So now let's talk about the next sort of lowest temperature. So we started at around 400 or so, and now we decrease the temperature, and the temperature is at around 300. So at 300, the liquid composition follows the boundary curve, and so it is represented by this point W. And so now, again, we still have 3 phases, and this is our triangle representing that, but the only thing that's changed is the liquid composition. We still have an alloy of X, and so we can calculate the amounts at those various points. And so this continues to occur until we reach some other critical point. So the liquid is continuously changing throughout this process if we decrease the temperature. All right, so the last sort of critical point, so we've been following the boundary curve down, and you can see it flowing towards the eutectic, right? So once we reach that point, and that point is 200 degrees here, once we reach that point, it follows the eutectic reaction. And so that's going to be the liquid. It has, if it's at this red point, it has the composition of the eutectic at that point. And so it's going to form alpha, beta, and gamma. And it's going to form a eutectic mixture, just like it did in a binary system. And so the remaining liquid basically transforms into that material, but it only does it at that point. And so that's sort of the last path that happens. So at 200, or right below 200, all of the remaining liquid has become a solid. And so at that point, there's no more solid. And so we basically cease drawing this curve, because this crystallization path that we're drawing here was for the liquid composition. And so that's something to keep in mind, is that it's showing you the liquid composition as we go through this. All right, so that's the sort of basic idea here in how we make these crystallization pathways that basically show us the changing composition of the liquid with the phase diagram. So what I want you to do now is pause the video, take a look at this ternary phase diagram that I've shown here. It's a little bit different than the one we just worked on. And I want you to see if you can sketch a similar type of crystallization path for a composition of A, but as that composition goes through the same process. So starting at when it's 100% liquid all the way to when there's no liquid left. See if you can draw that crystallization path for this composition on this ternary phase diagram. So pause it, come back when you have your answer, and we'll discuss the results. All right, we're back. We're taking a look at this crystallization path for this composition A. All right, so we'll work this one together. So let me exit out of the screen here, and I've got the phase diagram by itself here, and we'll go through how to construct this. So keep in mind, I'm going to do this on the PowerPoint, and so the curves may not look exactly perfect, but I'll try to make them as smooth as I can. All right, so the first thing to keep in mind is the position of the composition here. So this composition A is kind of halfway in between 1700 and 1600 degrees. So that tells me that it kind of sits on an isotherm for about 1650. So let me write that out for you. So that's kind of the first temperature that I see. All right, so that tells me at about 1650, then this composition would go from 100% liquid and to start to form the first solid. And that first solid is going to be based on the primary phase field, which is cristobalite, which is basically a phase of quartz. So that's going to be the first thing that I see. So at 1650, the composition is going to be the composition of A. So that's how that's going to be the composition of the liquid. And then the solid is always going to have a composition of cristobalite, which is pure SiO2. And so if I do that, so let me make a line here from A to, so effectively this is my tie line, and I'm going to make it dashed. So that's kind of, so this is the solid composition, and then right at 1650, this would be my liquid composition, right? That's what this is telling me that I have. And so the reason I also drew that is this also, if you're wondering the direction of that crystallization path, the sort of the vector that you saw in the previous example, if you're wondering how I got the direction of that, I get that from this as well. So now if I go below this 1650 and I start approaching lower and lower temperatures, the temperature of the liquidus, or sorry, the liquid composition changes, and it follows the curve of the shape here. And so what I can use is I can basically use the extension of this line to show where my liquid composition is going to be. So as I decrease in temperature, let me make a new shape here. So as I decrease in temperature, my liquidus temperature is going to extend that line. And so let me see if I can make this look good. So it's going to follow that extension from A. So it's going to look something like that. So it's going to start out at A, and then the liquid composition is going to follow the trace of this line. The solid composition doesn't change, but the liquid is going to follow this crystallization path. So let me make this an arrow. All right. So this, so basically from 1650, we're going to start to form the solid phase cristobalite. So we're going to have L liquid goes to cristobalite plus second liquid, and that's going to happen, and that's going to go basically until we get to this 1400 degrees Celsius, right? So that's the point at which we reach this boundary curve, and so something else is going to happen. So at that point, the boundary curve serves as the new liquid composition line, and so that's why it's going to switch, and it's going to go towards E here, because we now have this new En phase that forms, and so the liquid will follow this path. Because again, remember, this is a projection of a 3D thing that we're trying to show in 2D. And so if this is confusing, maybe go back to that original image, 3D image, and see that basically what I'm trying to show here is the liquidus curve. I'm trying to show you the surface of that and the way that it happens. So this is the projection in the 2-phase field, and then the 3-phase, it's going to follow that line. And so we're going to have a line. I'm going to just draw this one that starts here and then follows the boundary curve down, and it's going to keep following the boundary curve down until it gets something else significant, which at this point is the eutectic temperature. So this is path 2, this is path 1, and so path 1, if we just revisit that real quick, this is where we had liquid goes to a different liquid L prime plus cristobalite. So I'll just call that CR. Path 2, this was the L prime goes to cristobalite still, but also En. Plus, there's still liquid, so L double prime. So those are our kind of 2 paths that we have so far. And so it's following the boundary curve here for the second path. So once we've reached the significant temperature, though, at E, this is basically 3. So this is the lowest temperature. This is, so this is 1400, this is 13. So this would be lower than 13, so we can call it 1250. And so at that point, we reach the eutectic reaction. And so L double prime is basically the eutectic liquid. And that goes to all 3 solids. So CR plus En plus the 3rd phase, which is this AN phase. All right, so that's what we can kind of expect. And this is, again, this is what we call a crystallization path. And this shows us the liquid composition at any point. And so the reason that we wanted to construct this is that now we have a pathway. We know we basically followed the liquid composition along. So any point along the way, if we're asked a question, for example, at 1400, 1300, whatever the temperature is, we can know what the liquid composition is for phase amounts calculations with the lever rule or anything like that. We already know what that is, and we can use it for those types of calculations. All right, so the next thing I want to do now that we've done the crystallization path is to go through and see if we can set up a problem that asks how many phases we have at 1300, and then set it up, but you don't actually have to solve it, for how to determine the phase amounts at that same temperature of 1300 degrees Celsius. So again, pause the video, do what you need to do to print it off or do a screen capture or anything like that to be able to work this problem, and then come back when you think you know what you have, and then we'll work through this together. All right, so now we're going to go ahead and work through this together. So, excuse me, I've got a blank diagram, and we might also refer back to the crystallization path that I had before. But the question is asking about 1300 degrees. So let me go ahead and go back to the crystallization path we just worked on. All right, so again, if I'm looking at all of this, I see again that this crystallization path tells me the liquid composition. That's all it tells me. So if I follow this in terms of temperature, I didn't write out the temperatures fully up here, but you can do that as you work through this as well. This was 1650, and then going down to 1600, 15, 14, and then at that point we switched to path 2, and so below 1400 we're in path 2 until about 1250. So that 1300 number should show up in path 2, right? So somewhere along path 2, and it turns out to be right here. And so let me go ahead and duplicate this slide for us, and I'm going to use that for this next problem. So we'll ignore that blank one here. So we've got the so now we have the that's too big. So now we have we're looking for what happens at 1300, and so again 1400, and then the next time we see it, it should be 13. So basically right at that point, right? This is 1300. And so this is our liquid composition at 1300. So also though, think about what else we have. At that, along this pathway, we are forming cristobalite, this En phase, and we still have liquid, right? So there's 3 phases in equilibrium, the Cr, En, and then a liquid. Right? So we have 3 phases, and so we're going to need to do the ternary phase rule, right? And so with that, we're going to have to know 3 compositions. Composition of the liquid, and that's what we get from the path. So basically this is our the point on our crystallization path is our liquid composition. And then we need to know the composition of the 2 solid phases. And so En is right here. This is where En shows up. And then quartz, or QZ, is cristobalite. And so those are our 3 compositions. So let me highlight those. So this is one composition, and then we have a composition here, and then also here. So that's going to be our triangle that we use for these calculations. So let me draw that out for you. So if I connect those dots that we just made, and let me make those red. Make another one. So this triangle that we have is going to be the triangle that we're going to use to calculate phase amounts for those 3 phases at 1300 degrees Celsius. And if you're wondering what our fulcrum, our compositional point is going to be, it's always going to be our composition, which is A. So this is our composition A, which serves as our point. And then we have our 3 compositions, and we're going to calculate the phase amounts just like we did in the previous examples, but just using this specific triangle. So again, I'm just going to show you the setup here, but feel free to go through and work this out and get the actual amounts if you want to.